So as I said last time, there are three distinct cases for this equation. And for now, we're going to assume that f equals 1. There's not a second daughter. We'll get into that later for complex decay. For now, we're just looking at compound decay. Okay, so this is what's called secular equilibrium. This is when the lifetime of the parent is much, much longer than the daughter. Or I could say that the decay rate of the parent is much, much less than the daughter's. Remember, the decay rate and lifetime are inversely proportional. The longer your lifetime, the shorter your decay constant. Sorry, the smaller your decay constant, and vice versa. So what will happen in this case is because the parent is lasting so much longer than the daughter, eventually the daughter's activity will match that of the parent. And this looks a lot like our previous example. However, we're not going to have that shut off in production because the parent lasts so much more than the daughter. If you're wondering why this builds up to the parent activity and not past it, it's because the parent's activity is what is producing the daughter's. And so what we're doing here is eventually we're getting to the point where there's so much of the daughter that its activity equals that of the parent, because if its activity equals that of the parent, that means that the amount going into the daughter is the amount coming out of the daughter as well. It's equal. It's reached equilibrium. Okay, so that is if the parent is much, much longer lived than the daughter. What if it's just a little bit longer lived than the daughter? Well, that's what's called transient equilibrium. So in this case, you can see everything looks very, very different. And the reason for this is because now we begin to see that the parent will decay. Its lifetime is finite. That one wasn't infinite, it's just very, very long lived. And so it's going to decay along with the daughter, just a little bit slower than the daughter. So when this happens, you will eventually have a point where the daughter's activity will surpass that of the parent before they both drop off. That happens right about here. And you can also see that there's a max point for total activity that happens that is not right at the beginning. It happens a little bit after when the daughter is being produced and the parent is dropping off. This kind of the sweet spot right around here before they begin dropping off. And once they've reached that max, both will start to decay as the parent can no longer produce enough to keep the daughter going. The cool thing for us is if you solve our differential equation, our equation for the lifetime of the parent and the daughter, you can actually figure out what the max time is, when that point we're going to have the max amount of activity is. And it's equal to this equation right here. I'm not going to go through the derivation right now, but you can if you want to later. The last one is simply no equilibrium, which simply means that the parent is got a shorter lifetime than the daughter. So every single bit of the parent is being produced. It's dropping down really dramatically. And so the daughter is going to quickly dominate here because the parent is dropping off so quickly. So all the parent becomes the daughter species and it drops off. So you can see that right here. The parent is dropping off really, really quickly. The daughter is quickly produced. And because it's longer lived than the parent, it will dominate the activity after a while when the parent has gone down to 0 after about 7 half-lives. So, went too far? This is it for this time, and next time we're going to go through an example looking at how we can use these equations to solve some real-world problems with radioactive isotopes. Thanks for listening. I'll see y'all later. Bye-bye.